All right, good afternoon. It's my pleasure to welcome you. Our speaker today is Don Syme, who got his PhD from Cambridge University about a decade ago, maybe not quite. Since then has been at Microsoft Research. If you have used a generic in C# or in Visual Basic, you have Don to thank. He added it to the CLR, to .NET, so you could use that stuff. He wasn't happy enough with that. He said, if we're going to have generics, why don't we have a decent functional language to use them in? So he went off and added that. It's now a product. It'll ship with Visual Studio 2010. He wasn't happy with that. He said, now that we have a nice functional language, let's have a way to write parallel and reactive programs in a nice way. And I think that's what he's going to show us today.
Yep, that's right. OK. Right, thanks, everyone. Is the mic on? Can you hear me? Yeah, it's all on. OK, great. So I'll explain a little bit about how I came to be here today. Firstly, I haven't actually done many talks in US universities, surprisingly, over the course of the last 12, 15 years in computer science research. And we finally got to the end of this effort to make F# in Visual Studio 2010, and we got talking to Burton Smith, and Burton Smith said, why don't you go give a talk at Berkeley? And we got talking to some people who wanted to hear about F# at Princeton and the like, so I just emailed around to the university relations people and said, look, where should I go and give a talk? And they said University of Washington was first on their list, and that's by far the easiest because I'm often over here visiting the guys on the team, two of who are at the back. So that's how I got to be here, and I said, at University of Washington, when I've known Dan for quite a few years, and thank you very much for having me along. And so I'm going to be giving an overview of F#. So I would imagine it's a bit hard to get a measure. How many people roughly would know what F# is and sort of why Microsoft is doing it? OK, that's actually quite a lot more than many of the audiences I think I've been giving talks at. So I'll be pretty brief on the overview. And then we'll try and talk about the asynchronous and parallel programming topics. So I'm actually going to run over these slides. I think you know the sort of rationale for what F# is about. Just drawing out the three main themes that we're dealing with in trying to hit the sweet spot with a functional language on the .NET platform. One is about making certain classes of programs just a whole lot simpler to write. The next one is just about the economics of adding something to the .NET platform. This is sort of an argument about why we don't do Haskell, for example. It's a little bit harder to, say, make a .NET version of that. But it's also, if you don't do a .NET language, then you miss out on a lot of the network economic effects on a platform like .NET. With F#, it's a relatively small investment. With 10 people, we managed to add a functional language to the platform, working over a couple of years and a 5-year research project before that. But from that, we get to use all the debuggers, all the virtual machine, the just-in-time compilers, the garbage collectors, all the libraries, and everything else you get in the economic systems, in the ecosystem. So it's really about bringing functional programming into .NET and bringing .NET to functional programming. Sort of these two worlds that were quite a long way away from each other before we started this line of work. And parallelism is actually a major factor for why we're adding F# to the platform. The overlap between functional programming and parallelism can be subtle and complicated. I mean, it's not an automatic silver bullet for solving the parallelism question, certainly not. But I'm going to spend a bit of the talk trying to draw out what functional programming does bring to the parallel programming problem. On the simplicity slides, I'll just show the standard sort of comparisons between C#, the pleasure and pain slides that we have here. Different people have different takes on object-oriented versus functional. A lot of people just like writing the short stuff. Some people like using very structured object-oriented techniques from the moment they start writing their program. But from my perspective, I tend to be more on the kind of left-hand side, just to keep things simple. And you just take standard object-oriented design patterns, like one of the Gang of Four, the modeling the notion of a command. You kind of write it out in these functional programming languages, and it all looks pretty straightforward and simple. We have break commands, turn left commands, making some action on this rover object. And then you write it out in OO, and it just kind of goes on and on using the typical OO techniques. I mean, so we add things to C# and the like to make it, you add delegates and so on to be able to do what you have on the left. But the point is that OO itself, this is really an argument about the pure OO methodology versus like the functional programming methodology. And you take other examples and it goes on like this, and you kind of have very simple programming with tuples and lists and just the routine day-to-day process of taking data, making transformations on data, writing out that data in some other format tends to be just very, very sweet in these functional programming kind of languages. And you can do good programming in C# and in Java and the like. It's got a lovely system of generics, but there's all sorts of programming which just feel a little bit too painful to be doing this in. To be taking this approach. Okay, take other examples, the typical abstract syntax tree kind of examples. This example goes down into the basement somewhere for the object-oriented ones. It spills off. I always get comments after the talks from the guys doing the videos saying, was that meant to spill down into like that far off the bottom of the slide? I say, yes, that's how it is. And you just do further examples like this. On the parallelism sort of simplicity as well, this is like how you do a parallel fetch of web pages. I've actually fudged a little bit by presuming there's a function called getPageDefined, which defines an asynchronous action to go and get a web page. And you want to get these pages in parallel, and without start spinning up lots of threads or something, you just specify the asynchronous requests, put them in parallel, you get a new asynchronous request, which you can then compose with other operations as well. And you don't even bother putting the C# code for this. If you do C# programming with locks and background threads and thread pools and so on, it really goes on for a very long time. And just say you might have a CPU set of CPU tasks as well, creating 201 CPU tasks and putting those in parallel. That puts them in a queue and does a fork join on those. You can think of this parallel as a fork join operation on these tasks. And just to say, if you actually do this in F#, you also have to actually run the composition of the tasks, which you do by piping it through this async.run synchronously function to get the actual value out. So just a little example of how that simplicity in solving, it's a simplicity in solving problems, a simplicity in manipulating data, and how that translates into the programming language. We often characterize F# as a language which is suitable for data-rich applications or control-rich applications. If you think of asynchronous programming as being a control-rich application, then those are the sweet spot. We don't advocate the use of F# particularly for what we call presentational programming, doing your designer kind of work, the things doing your user interface work, your Silverlight or your web page design and the like. So we're more focusing on those background components, those DLLs that do the interesting, smart analysis on the data, for example. Okay, just to give a bit of a taste for its influences, we have two streams of programming language history, OCaml and C#.NET. You can see the core language coming from OCaml and the object model coming from C#, which itself is strongly related to the Java object model historically. We also have influences from Haskell and many influences coming in from Haskell as well in the asynchronous programming work. So it's really a multi-paradigm language between functional and object-oriented. And it is an impure functional language, so you can do all the things you can do in OCaml or in C#. That does translate methodologically into how users feel about it. It's more of a functional first language, quite a lot like OCaml. Functional programming is your first point of call for problem solving. So you can see that translates into how people talk about the language, how they use it. So it allows you to move from functional code and where necessary, move into object-oriented code for structure, and then use imperative programming where necessary for performance. And that does correspond to transitioning from having an idea and moving through to realistic code. So it's a functional programming language for developing ideas, doing concept development, but it has enough object-oriented programming to let you transition into structured, well-structured, good quality software engineering code. Okay. Right, so let's just take a look at some simple F# programming and then move on to the async and parallel work. Okay. Right, so we have here actually Visual Studio 2008. For various reasons, I haven't got 2010 running on this machine, but using Visual Studio 2008, you can get Visual Studio 2008 for free using the Visual Studio 2008 integrated shell, and then you just plug F# into that, and you can get what we're using today is a free for use development environment. Okay, so we've got at the top here just some code here. Let's close this, close all about this. Down the bottom, do a reset down here. We've got F# interactive down the bottom. So we can take, we can do the usual kind of thing. Take a right line, hello world. We can take fragments here and execute them. They get executed in the window down below. We might print in hello. Again. Okay, we might create a form. So I'll put it topmost equals true. Okay, form dot. Okay, so now we might say add a click handler into the form. Just do the usual functional programming thing of using functions as the event callbacks for an event. And so every time we click on the form, we print I was clicked. Okay, so we've added that event handler, highlighted that, and now each time we come over to the form, you'll see I was clicked coming out down below. Okay. Right, so we're going to just do some simple data acquisition. So I have to open the namespaces up here. We're going to use the .NET libraries to create a web request for a page. We're going to get the response, and we're going to get a stream reader, and we're going to read that to the end. Part of the reason why we're going to do some web requests is later on in the talk, we're going to be doing asynchronous web requests, and you'll see how to write this code in the asynchronous mode of F#. Okay, so we run that code. You'll see the HTML for the start of the Yahoo homepage for the 125K of the HTML comes back to us here. And we can say get the length of that and find that that is 125K long. Now we can wrap that up into a function here, which is going to, for any URL, given the URL that's the input here, it's going to return us the HTML for the page. So for instance, we can go get the HTML for the Bing page or the Google page or the newspaper I read back in Australia, and one for the New York Times here. And let's just go up and delete that code that I started with up here. And now we'll create ourselves another form here, and we're just going to use this to display some data. So we'll create a text box and we'll add it into the form here. And now we're going to have a function here called show, which we can use to show any kind of data in the form. So we can take a tuple and display it up in the form, up in the top right-hand corner there. Or we can take the list of the numbers from 0 to 100 and display those in the form. Or say the floating point numbers stepping by 2. Moving down a bit, you'll see something you'll see quite often in F# code is this pipelining, where you take some data and pipeline it into a function. That's just function application. Just take an object and pipe it into some function. And it will do the same things with this data. We might make a table of squares for each of the numbers between 0 and 100, generate the number I and I times I. Or we could do the same thing using a slightly different syntax. And we can go through other examples of that, of just generating some data. But let's look at a different kind of data where we have the RSS for the New York Times. So this is the RSS for the latest headlines from the New York Times. And we can do the same kind of data manipulation and querying where we select all the inner nodes for the titles. For instance, there's a title node there, and grab the text out and use the same kind of query processing to find out the actual titles in the XML. And then for each of those nodes, we might want to say find the ones that contain a word, usually like Obama tends to feature these days. So you get three headlines this time, up on the top right-hand here. Okay. So similarly, we can say do some manipulation on the web pages to say collect the links from the web pages, just using, again, the .NET libraries here using some regular expression matching. We extract out those links, and we get the list here. We'll do that for a couple of other web pages. And now we're going to put the pieces together and make a synchronous crawl of the internet, where we say we do a depth-first crawl of the web here. So this is just a simple depth-first recursive crawl function, which takes a function to visit each URL in the web. Okay. And we're going to limit ourselves to 12 nodes, and we can do a crawl and print, say, starting from Google, and we go through and start crawling the pages on the web. Okay. We're going to display that data in a slightly different form, just because I'll use this form later on in the talk, just using a grid display. So it's a visualization technique I quite like. Okay. And we'll do the same crawl, doing an update of the display, and at each point, we're just doing a synchronous request for page after page, and then displaying the URLs and the number of links that we find on each of those URLs along the way. Okay. So, so that just gives you an idea for a sort of use mode of F#, which is data acquisition, functional programming to do data transformation, followed by visualization, analysis of that data in some kind of form. We kind of think of that kind of programming as being at the heart of what the online services division at Microsoft do, as well as, of course, having on the data analysis side of their work. They will take lots of log files, do lots and lots of statistical data analysis on the contents. It's also at the heart of a lot of the kind of programming that Google obviously do for in data manipulation and analysis of web-based data. And it's a very sweet use mode of F#. Okay. So I'm going to show you what is a fairly famous F# demo, but we're going to have a slightly parallel twist on it at the end. This is a demo called the Microsoft, the F# DirectX demo. The sample sits on around 300 lines of F# code to drive these things called the managed DirectX libraries. And the managed DirectX libraries are fairly low level. They're a thin layer over DirectX, so kind of creating the triangles for a 3D display fairly manually. The helper library we have defines some additional helpers to draw more interesting objects. So we're going to go through and call those helpers. So the first thing is we create ourselves a display and put it on this form. And then we're going to make sure we can see the code here. Okay, it's a little bit too, put it down here. Okay, so the first thing we do is we draw a cube axis on the display, but we have to set up the lights as well. And now we're looking down on this mesh display. And we can set various parameters on this object. F# is about state minimization more than pure functional programming. That means when you have a user interface components, you have mutable state, which you can change and you can adjust the display. Okay, so that's what we're doing here, where we're adjusting the display by kind of setting the objects that are being displayed and the triangles and the functions that make up the scene that we're displaying. More than actually, we're not doing a fully functional approach to this. The user interface state is imperative. And now we're going to listen into the mouse positions as we move across the display. We're going to listen into those events, and we're going to adjust the display as we go. So we have the mouse positions here, and each time we move, we adjust the view display so that as I drag the mouse across, you can see the view parameters are being modified by this line here. Now the view parameters are being modified by computing how far we're moving so that as we move left and move right, the display gets adjusted. And depending whether the button and the modifier keys are left, shift, or left, and so on, we adjust various aspects of the display. We adjust the yaw pitch roll or the focus or the zoom. Okay. So now we can display a surface on as well. So we can, upside down. Yeah. So here's the function that we're displaying here. It's a function of the x and y coordinates here. So maybe use a different function or say a function that depends on time as well. So at each point in the simulation display, we're calling that function for each of the values in the mesh, and we're creating the mesh and sending that as a specification for the triangles across to the display engine, which then uses that data to generate the display. We can say evaluate it at a slightly lower mesh or a thicker mesh. Maybe change to the ripple function here. So now we're going to do that. We're going to do a bit of simulation, and this is where we get to the parallel side of it, or it's just a touch of parallelism. We're going to have a data structure here for representing balls that are going to move around on the surface, and the balls are going to be made up of a pair of position and velocity vectors. And then we're going to have a function to move the ball, compute a new ball on the surface. I'll skip over that, and to draw the ball. And then we're going to have a simulation engine. Okay, so the standard task in doing this kind of simulation engine is just to have a background agent which accepts messages. You can send it messages to say, like, take one step of the simulation, please. Or you can send it a message to add a ball into the display. So you can see the message type that we're sending to this background agent. Nice packages of messages, immutable data that we can't change, that we can just send across to the agent as a specification of the actions it should take. So that's good. The simulation state is just a container for a state that's not very exciting. That's in the helper library. And now here's our background asynchronous agent, which is our engine. So it's an asynchronous agent in that it sits there waiting for messages. Okay, so we start an agent, and it's an asynchronous agent, and while true, we sit around and wait for a message, which is this magic line here. So that's just reading off the message queue. And we take the message, and if it says, please take one step, we transform the state. And if we please add a ball, we add an object into the display. So let's take that simulation engine here and define that. And now every time we render the display, we send a message, we post a message to that agent saying, please take one step. Okay. And every time we draw the scene, we take a snapshot of the objects from the simulation engine, the state of the simulation engine, and we draw a ball for all of the functions at that snapshot of that time, for each of the objects at that snapshot of that time. Okay, so now let's set ourselves the surface here. Now we create ourselves a piece of data to represent a ball in one corner of the engine, and we post that ball up in an envelope, send it across in a message to the simulation engine, and now we have that there. So it's given to the simulation engine, and the simulation engine is sitting there getting the request to update the display. We're taking snapshots of the display and drawing the ball as the simulation progresses. Okay, so this time we started up a second agent here, async.start. On an agent, we can read its specification here, that agent from 0 to 6. So for 7 balls, add 1 ball in the top right-hand corner and do an asynchronous sleep for 100 milliseconds, so the ball's going to slide down. And we keep tossing balls into the display, and they progress into be this ball train in the display. So we could add a few more of those in. Okay, and finally we make it a little bit harder by making the surface move, and everything goes pretty chaotic straight away. Okay, so I hope that's I think a classic and I think quite a sweet demonstration of how agent-based parallelism works in a typical desktop simulation kind of application. There's lots of other topics we need to talk about in parallelism, so we should move on to those. Okay, so let's take a look at the sort of the overview of F#. We have a functional core language, we have an object-oriented extension, and we have functional data structures like lists and maps and sets and tuples and the basic building blocks of functional programming, records and unions. And now on top of that, I want to see what we add to this basic core mix. This as a core language it's a wonderful I think a wonderful core functional programming language. There's one thing we add which is very much in tune with this kind of typed functional programming, which is a thing called units of measure, where you can annotate your floating point numbers with kilograms, meters, and so on, physical quantity kind of scaling quantities. But that's a little bit off topic for today, so I'll skip over that. There's one big compromise we make in F# from the programming language perspective, which is we add imperative mutation and I/O. And that means you can do I/O at any point. You can mutate imperative state at any point. But it's that said, there's a lot in the methodology and in the design of the language which leads you to sort of what we call this state minimization, to use a lot less. As you do problem solving, you naturally find yourself eliminating most of your mutable state and using other representations instead. Now, on top of this, we add a feature called computation expressions, which you can think of, for those who are savvy with Haskell, think of as a monadic mechanism. But this is really for expressing these asynchronous blocks that you've seen, these agents, these things that wait for things and then do a bit of work and then wait and do a little bit more work. And we also add this feature for doing queries in the language. And it's one of these interesting programming language features which you only use it for about 2 or 3 things, but it's incredibly important for when you do use it for that purpose. And the other thing we add is a system of meta-programming where you can take expression trees or syntax trees for chunks of F# code. And this is actually really a very powerful feature. I won't be talking about it much today. You'll see a couple of short examples of it. I'll skip over the object-oriented programming and the data structures. And we'll look at just one kind of example of meta-programming in F#, which is where we have a meta program here where we're doing, where we've got a query here to analyze some database tables, so database.customers, database.employees. If the countries are the same, then yield some data here, this tuple here. So this is very much like a query, a database query. It's a join between the tables. And you can take these and put these little marks around it and put query out the front. This is using something called the F# Power Pack, has an implementation of this query operator. And then this sends this off to the link engine on .NET, which then executes this as a database query on a database. So it's an example of the use of quotation metaprogramming to run your F# code somewhere else in a slightly different kind of way through an engine. And this is related to our philosophy about parallelism, and I'll come to that now. Right, so let's talk about parallel and reactive programming in F#. So people tend to have a fairly loose definition of what functional programming is. So when you talk to people about functional programming, you'll get some people who say this, who that functional programming is sort of anything that isn't imperative, more or less, which means that anything without explicit use of mutation. So I think that's a bit too broad, but I'm not going to actually try and pin down what we mean by functional programming. I'll deliberately keep it loose. But what do people usually associate these things with functional programming? Programming with immutable data. Maybe they'll think a lot about query kind of languages. They'll think of SQL as sort of a functional programming language. They might think about Excel as a functional programming language as well. Because I think in the case of Excel, the key thing is the actual formulae don't update other cells, okay? Even though the actual evaluation algorithm is somewhat not so easy to understand. It's the key thing that the program itself isn't about updating the data in the program. They might also think about a strict definition, that it's a language which has lambdas. They might also think about pattern matching, lighter syntax, or type inference, or taming side effects in general. So why is functional programming suddenly becoming more relevant at all? And this is the trends that I think are important. First of all, there's a lot of communication with immutable data going on. We have whole scenes, even in devices, we have the presentation layer now being described using immutable data. Okay, you create a blob of data which represents the display to be rendered on the screen, and then that gets rendered in some way. Let's think about HTML. Every time you do a web page request, you're getting a whole copy of that HTML back. You're transferring immutable data. You're not making a connection to the server where it actually mutates something on it gets a handle to an interior pointer on your machine. You're communicating with immutable data. And you see this trend all the way through, and that just makes functional programming sort of more relevant because it's less about controlling the state of your one machine, one device. It's more about communication and transformation. We also see a lot more, many languages about just querying data. You can look at MapReduce as well in Google as being an example of this. You've just got lots of data out there, and half of the work is down to querying that data and analyzing it, rather than, again, doing the imperative programming and the mutation. I mean, on the programming languages side, there are just lambdas absolutely everywhere, and pattern matching is becoming a lot more fashionable in languages. Languages with a lighter syntax and with type inference. So in a sense, F# is about giving you a language with a light syntax, but recovering the type inference. And in terms of taming side effects and minimizing side effects, we see I think particularly, I mean, we should talk about isolation in Erlang is just an amazing thing. The fact you get an isolation guarantee for the agents that you're writing. And in Haskell, the whole effort to just try and minimize the side effects in your code in order to simplify the problem of concurrency is a key trend as well. So two things are driving each of those things that I described, which is the web and multi-core. Okay, and these together make a transition towards functional programming in this massive scale of the kind of Google MapReduce kind of problem, and on the sort of much smaller scale, but still very complex scale of these multi-core machines. Okay, and as well as there's always the historical thing that functional programming is actually an amazingly enjoyable and productive paradigm to be using in your day-to-day work. So let's talk how that relates to parallel programming. We have less mutable state. So these are some of the things that make up typed functional programming in the programming language perspective. So we have this consistent focus on just eliminating the use of mutable state where it's not necessary, or controlling it where it is necessary. We have types, which I won't talk about so much. We have these embedded computational languages and embedded declarative languages. Okay, so let's look at those. Let's look at these one by one. So when we talk about less mutable state, we'll talk about isolated state, purity, minimizing state, transactional state, and immutable data, and there's probably other things you might put under that category as well. When we talk about types, you might talk about things like generics. When we talk about embedded computational languages, we might talk about combinators or monads or monoids. By monoids, I mean query syntax. And on embedded declarative languages, you might talk about meta programs or DSLs, or LINQ as an example, which many people are familiar with. So in this one, so what role does this play in parallelism? Well, I think, in my opinion, if you just take the standard imperative programming as we have it today and really talk about parallelism, I mean, unless you talk about some of these research kind of advances, so which is like Dan is working on making modern concurrency deterministic, for example, if you just take non-deterministic execution of imperative multi-threaded code today, it is just such a nightmare to write that kind of code that we have to do something here to make that kind of problem tractable. In types, that just makes programming sane in general. I've got a bit of a bias in that one, so. In embedded computational languages, in F#, what we're bringing here is effectively to embed languages which simplify the process of control. So you saw that async.parallel at the start of the talk. You effectively have an embedded language of asynchronous computations. So you're making task parallelism, the tasks of fetching those web pages, you're making that compositional. You can specify tasks and put them together in effectively a little embedded computational language, and then press a button on that network of tasks and get the result coming back. Now on the embedded declarative languages, this is where the F# philosophy is a bit different, say, to the Haskell philosophy. In the Haskell tradition, there's always been this kind of hope that you will get automatic parallelism of Haskell code dropping out. That's a good research, it's a very important set of research. But the hope more for F# declarative parallelism is that you have these embedded declarative languages where you specify queries or array or matrix programs or constraint programs, and that you take those and maybe you specify them using F# syntax, and you send those off to an engine, like a database engine, which will execute them in parallel. Okay, you send them off to your GPU. You use them as specifications of a GPU, using a library like the Microsoft library called Accelerator or other similar libraries. Or you might have a little language which specifies linear constraints, linear integer programming constraints, and you give them to a constraint solver which can execute those in parallel. So it's deliberately designing a language which has engine-based parallelism as one of the key aims, the key targets for how we exploit parallelism. Okay, just to see how that might appear in F# code, you actually write async. If you like, you can think of that as task, if you like. But similar on the embedded computational languages, you might see what's called a parallel sequence.map or async.parallel as being manifestations of that kind of parallelism. On the right, in the declarative engine-based parallelism, you'll see what I showed before. You'll have a query of some kind, which is a meta program being executed through a parallel programming engine. Okay, so if we look what F# is bringing to parallelism, then on the shared state question, we're bringing immutability. On the inversion of control, so there's this problem that in typical task-based parallelism, then all your code ends up upside down. And any code that has to react to messages from the outside world, then your code ends up upside down. And that's what this F# async feature is for. And for implicit parallelism, we talk about engine access and embedded languages. And on distribution is not something that F# addresses directly. It's not a distributed language sort of when you get it in the box. You have to use something like Azure or use Amazon or any of the other cloud-based services for doing distribution, or do your own communication and distribution. Okay, all right. So let's look at these. I haven't got a lot to say about immutability, except that there's lots of immutable data structures around to help you to help tame the shared state problem. In the DirectX sample where we had the balls floating around, the simulation state was represented as immutable data. Okay, so at any point we can just take a snapshot out of the simulator and use it in the user interface because it's totally immutable data. It's being updated. The whole state is being updated, but we can take a snapshot at any particular point in time. And so that just eliminates a huge class of bugs in your program when you use immutable data. Okay, so now let's take a look at F# async on this inversion of control and I/O task agent parallelism. Okay, first of all, we have to think about how we should change our view of a computational model. When you think about functional programming, right, if all you could type was functions, let f of x equal this, then you haven't got any chance of having parallelism there, except implicitly, okay? It's not a parallel language yet, okay? Now, F# is a parallel language because there are various ways to start multiple active function evaluations or expression evaluations. So the traditional view is a functional language is just computing one expression, but no, okay, we can be reducing away on multiple expressions at the same time. So F# is also a reactive language, and that means you've got multiple pending reactions. Okay, so somewhere in the system there's a way to put away functions which will get called back when events happen. I mean, we're all used to this as working programmers, but it's not that common that in your view of how you describe a language, you actually separate out these notions, right? That, okay, we've got active computations, which correspond to .NET, executing .NET threads, and we have pending reactions, which are going to wait until other things happen. And it's important we separate these out because we're living in a world of .NET and virtual machines where the active computations are expensive. .NET threads, operating system threads, Java threads or whatever, they are relatively expensive. We know that. They're 2 megabytes for a stack or the like. On the other side, we've got, but there's an advantage over there because the code actually runs really fast, right? It runs as fast as C# code or C++ code quite often. So we're able to, exploit, and it can interoperate. When you're in the world of threading, active computations, that's great because you can go and make calls to .NET libraries and do all sorts of interesting things. The good thing about reactions, callbacks, is that they're cheap. They're a single object. right? They're just like one allocation at the minimum, but maybe they contain pointers closure to some other state. But relatively speaking, they are cheap. Okay, and we'll see that later on when we create like 100,000 or 1 million agents on a machine. Okay, so you couldn't have more than 1,000 or 10,000 or whatever threads on a machine, on a process, but you can have 100,000 of these pending reactions. These agents are going to react to inputs coming in. So what sort of inputs are we talking about? Maybe GUI events or page load events, timer callbacks, query responses. We've sent something off to the database and we're waiting for the request to come back. We've asked for a web page and we're waiting for the request to come back. We have some web service that we've called, or we've made a request to the disk and we're waiting for that to come back. Or maybe we're just an agent and we're just internally in the program and we're hanging around waiting to get a message, like the simulation engine was just waiting to get a message. And all of these are seen as reactions in this async programming model you can use from F#. Okay, so that's the syntax, you've seen that, a building block for writing reactive code. On the inside here, you can place any expression, okay? There's some rules about that, but the idea is that the control flow structure of the expression that's on the inside here becomes interpreted asynchronously. You can think of an async as a bit like a closure. You can press run on it and it will run some code, but you can it may take a while, and it's the sort of thing that when it finishes, then the person will go and do the work. You can get on and do your own work, but they'll call you back, okay? They'll call a continuation when the async is finished. Okay, on the inside, you get to do some extra things. You get to wait for events in this lightweight way. So that means you're going to react to some event, and then this async, the rest of the async will be registered as a callback to when the event comes back. So as I said, you just react to all those events that I listed off before. Okay. So you can think of it as a continuation monad. It's a one-shot continuations or resumptions. There's an async can result in 3 kind of actions. It will always end up calling either, assuming it doesn't loop, it will either call its result continuation, its exception continuation, or cancellation continuation. You can use exception handlers on the inside, which says that so they're what called delimited continuations, delimited exceptions and resources. You can put these things together using some nice combinators. You have this nice syntax for describing them, and you have some operations to start a task or fork join and some other operators, and you can build your own operators for piecing these things together as well. So you should really think of this as a building block for writing reactive code in F#. Okay, so we could have a little bit of an async code that doesn't really matter what it's doing. The important thing here is that we have an asynchronous action, like read a file asynchronously, and when that operation completes, then we register a lightweight reaction to that event. Okay, so that's a continuation or event callback. So there's a desugaring that goes on. You actually really don't need to know anything about it, except that it desugars into sort of a bunch of lambdas and functional stuff, right? So async.delay to make sure the side effects get run in the right place, async.bind to put the pieces together. So each of the let bangs corresponds to a bind, and an async return, it should say return image 2 at the end here as the argument here to return. And that you could actually write this code in C# today if you like. There's no really deep magic going on here. You just have to know the translation from the specification in a control flow way into a nesting of lambdas down below. Okay. So async is a very useful device. Let's say we have 2 I/O requests, asynchronous I/O requests, and we want to start composing these things. So you usually compose just by writing another async block for sequential composition. So now you can detect, we can detect the languages when that comes back. So this example is drawn from the Bing translation API, the Bing 1.1 translation API, but it could be any web-based API, HTTP-based API. You ask what languages the API supports, and eventually that request comes back and you have those languages. And then you translate, Actually, no, the first one takes a block of text and detects what language the text is in, comes back, gives you a language. You then translate from that language into Danish, giving that text, and then that comes back, and you return the text. So you're composing these things that react to events. So similarly, you can put some CPU computations in there. You can do the same thing and do some post-processing, for instance, as a CPU computation after the I/O requests. You can also just do regular task-based, CPU-based task parallelism. So for instance, you can compute the Fibonacci of two numbers and place those, say, in parallel. Or you might do parallel I/O requests, which is to do that translation from language to target to text, but do it for a range of languages and try and put that in parallel. Okay, so let's take a look at that sample. Okay. So here we are in the same setup we had before. We'll open up one of the forms here. And we'll define ourselves a little helper function. Run synchronously is the thing we use to actually run an async. It's like giving a job to your builder and actually waiting for him to actually finish and not doing anything until it actually comes back. So it takes an async here, async of some type here, and just returns that type there. Right, so let's open some namespaces. We'll do some very simple async programming first. We'll take the async program that returns 1 + 1, and we see 2 coming up here. That's nice. We'll take one here that, okay, this one shows that when do the side effects happen. When I define program 2, nothing happens yet. It's like a closure. Nothing happens until I actually run it. Okay, so each time I run it, we get hello world printed out here. Okay, so just to give you an idea of when the side effects actually happen. So now we can take those and put them in parallel, and so we get 2 and 700 up the top here. We maybe do something more interesting where we make 101 jobs and we put those in parallel, but they're still not doing much work here, so maybe we do some Fibonacci programming in parallel here. Okay, great. Okay, so we'll turn timing on there. So let's take a look at how that's just some CPU parallelism. We have 1 point. So there in the parallel version, we had the task parallel version. We had 2.8 seconds of CPU running in 1.5 seconds of real time, and we do the same thing sort of synchronously. Then it comes back so we've got to speed up close to 2, but it's not a balanced problem, so we would expect that not to be a perfect speed up. Okay. So now we're going to do some asynchronous web requests. So earlier on in the talk, we learned how to do a synchronous web request, and now we're going to do an asynchronous one here, which is very similar code. We just do a web request. We asynchronously wait for the response. We get a response stream. We read it to the end, and we return the text. Okay. So now we can take a set of URLs here, and we can do a synchronous fetch of those web pages one by one, and that's a little bit slower. So first of all, let's time that. Okay, let's get the timing value here. So that was 1.7 seconds. Or we can do a parallel fetch of those, and you can see that parallel fetch depends on your wireless connection and so on, but that parallel fetch comes back in half the time because we get some overlapping of the I/O requests to those pages. Okay, all right. So here we did an example of a little bit of post-processing. So we changed our parallel task to be not just a get. We actually get the text and simply return the URL and its length. So we do a bit of analysis on that data that we got back, and we just get the actual lengths of the various web pages. Okay. So in this part of the sample, we're going to be doing, using the translation API. So the first thing we do is make a request to find out which languages are supported by the API. So this is just a HTTP-based API, so we're just using a URL here for this Microsoft Translator service. We give it this application ID for permission to use the service, and we can call the service and make. There's 4 different methods on the service effectively. There's language detection and language translation. Okay, so we called one of the services, which is the language URI, which says what languages are supported. So we show that, we've got that there. The next one is to call the detect language service, which is creating a web request. We write the text in as a content, and we read the response off. And so, for instance, we can take the F# tutorial. Here we go, at University of Washington. Washington, yeah. Okay, and it's got it right, English. That's good, yeah. We'll see if I change it to UW, will it still know that? That's always, I got to admit that service, 1.1 of that service had a tendency to classify quite a lot of things as Danish for some reason, I'm not sure. But there's 2.0 out, I'm sure, so. Okay. Right, so there's a translation service which is similar. We're just making a URL here, and we make the web request, and we write the content, we read the response, and we put a try catch around just in case anything goes wrong with the service. This is one of the sort of things you can do in this asynchronous programming. So even though we're doing stitching various pieces of this service together, we can protect the whole asynchronous composition of asynchronous requests by exception handling. So we can now do a translation here from English into German. So in the next one, we're going to stitch those 2 pieces together. We're going to do the detection of the language. We're going to ask, here's the text, what language is it in? Okay, it's in English. Let's translate it from English into the target language. So we have the text coming in, we have the target language. We first detect the language, and from, translated, and this is all done asynchronously. Okay, so we detect the language of this text and put it into Dutch, and there we have it. So now, of course, we want to do a parallel composition of this. So for all the languages which a service supports, translate from the text, are you ready to learn F#, into the various target languages, and you make those requests in parallel. There's always a question of whether you actually get parallelism there, because the actual service might decide to serialize those requests and so on, but that's a separate issue. And then we display the results that are coming back. Okay. And let's do a graphical version of this. Okay. And now we can, say, press the translate button here, and it's making the request. And we get the text coming back. Okay. So there was one thing I'd like to mention here, that when we click on the button at the top here, when we clicked on the translate button, and we changed the text to translating, we started this parallel composition here, the asynchronous program, by a slightly different method called start with continuations, which says when this runs, call one of 3 continuations here. We have the success continuation here, the failure continuation, or the cancellation continuation. And so this is important because these continuations actually get run back on the user interface thread of the application, so it can do the updates to the user interface. Okay, and so then we update the translated text here, and we have the results here. Okay. Okay, moving on to the last topic on the asynchronous and parallelism, last topic of the talk, is to using this asynchronous mechanism to represent agents. You've already seen the example of this with the simulation state with an asynchronous agent that sits in a loop reading messages. So just to say the pattern, which is quite repeating, is you have an asynchronous agent with a while loop and a sort of read message function of some kind to get a message. Okay. So F# isn't the kind of language which says we have one notion of what is an actor, one notion of what is a process or an agent, okay? You can go and define your own message queues and your own agents that react to things, okay? We do have one built into the library called Mailbox Processor, which is a good thing, a good in-memory agent kind of mechanism. But as a pattern, you'll see the pattern repeating quite frequently. You might also write that in a functional loop. You have a recursive function where we have an asynchronous get message. He says, prints, I've got a message, and you can use this return bang as a kind of tail call to loop around do an asynchronous loop, waiting for some condition to be true. Okay, and so if you have some representation like this, of course you probably have a message queue underneath, and so that's a lot like an agent now, but you actually package that up. So you have some type called an agent, and you press start on it, and it can read its inbox and get messages from the world. And so this code works, you can type that into F#, but you do have to make so this type called mailbox processor is a good implementation of agents, and you can say type agent equals mailbox processor as a way of using that. Okay. Just to say, you can create lots and lots of those. You can create 1 million of those if you like, 100,000 or 1 million, and you'll just get a few objects allocated for each one. And you can start them all. So why don't we actually run this code here? Okay. Okay, I've got our alias down here. Okay, we have type agent here. We create our 100,000 agents. And now for each of the agents, we're going to post the message, hello. And you can see the agents, they have a message queue. They're not actually threads. They're just agents that when they get sent a message, it's a cooperative mechanism where their continuation gets scheduled to run and it churns through, and they all eventually get through and process their messages. And then they go to sleep again, and they're not occupying expensive resources. Okay. To finish up, F# is a general purpose, efficient, succinct, functional first .NET programming language. It has a simple, script-like initial experience, but strongly typed and is .NET friendly. Has some nice features for objects, async, agents, parallelism, and units of measure. And one really nice thing is it just interoperates with just about everything, and especially on the .NET platform, but through just about everything. And you can also build vanilla .NET components with it, where you don't know what language they're implemented in, apart from a reference to the F# library. So,
All right, why don't we thank Don again?